In this video, we're going to look at how we can utilize wedge tests in order to investigate the stickiness of collisions in our flip sim. So I want to investigate the stick-on collision parameter in the flip solver. So the probably the best approach is to set up a simple version of the scene that's similar to what you want to achieve for speed of testing, and then you can investigate how the different parameters that you want to test out will look. So I'll show you what I mean. Let's start by making another geometry container here, and let's call this stick to collision. And let's dive inside. So I'm going to make a sphere, and I want this sphere to represent our main body of the fountain, the big round bit. So as I mentioned before, the effect I'm trying to achieve is when we run water on a surface, it's not just going to fly off at an angle, it's going to roll round a little bit and then come off. And that's more prevalent in smaller fluid sims, smaller scales than the larger scales. So I want to investigate the various settings around that. So let's start with this sphere. Let's set it to a polygon and make it quite smooth. Maybe increase its uniform scale to 1.5. This makes it about 1.5 meters big. Our actual fountain's about 1 meter, so this is an approximately the same kind of scale. And I might just move it down a little bit, something like this. Let's make a null, and let's call this source. I like to color these red. Sorry, no, this is collider. So this is what I'm going to collide with. I'm going to make the source. I'm just going to copy that sphere actually and make this maybe 0.25, which is a lot smaller. We template this guy, and let's move this up maybe something like that, 1.2 above. And I might move it over to just over in the X slightly, just so it's not centered, just so it gets slightly more non-uniform splat. Let's just make a copy of this and call this the source. So I've got my two spheres roughly similar to the sim. I know I've got the fountain coming up and coming down, but I'm just going to have this water dripping down and then running around the edge here. And then we're going to try and get that stickiness of where it comes in a bit and then drips off. That's the effect I'm trying to achieve. So what I'm going to do is I'm going to merge these two together in order so that I can create a bounds for my simulation. So this is the two geometries merged, and let's create a bound node. And then that creates the bounding box around, just template that around the sim. Remember, I'm going to use this as the bounds of my container, because there's a little trick I like to use using a bounding object. So let's make this a little bit larger. So we want it to give plenty of space around the sides there for it to splash off. And I'm not interested in what comes below. I just want it to roll around, and then we want to see what happens around this edge. So I'm going to keep the, actually look, we need to increase the higher padding. Let's put the upper padding to 0.1 and the lower padding to minus 0. Lower padding, sorry, 0.1 to make it grow. It's a little bit lower. There we go, something like that. 0.1. There we go, so it's a little bit below the bottom there. Cool, because I'm not interested in what happens when it all flows down. I just want to see what happens when it comes around, the edge on this side. So, like before, we'll create a flip container. And we should have a similar res. Before we used 0.005, I think it was. So let's do 0.0075. So it's not quite as low res as our actual sim that we were doing, but it should be good enough testing. We could maybe make it the particle separation larger, which will make it sim that a little bit quicker if we need to. So what I'm going to do is just turn on the surface tension. And the reason we want to turn on the surface tension is to make sure it's similar in setup to the sim testing. I've got that turned on. So we want a source and collider. So we want our flip boundary. And let's plug that into the source node here. Just drag these a bit, just spread it out. So you see we've got the resolution ready for that. If we do a flip side, get it to collide with the sphere. Just like so. And then a flip solver. Actually, a quick way to connect these connections is if you hold down Shift and keeping Shift pressed, click on each of these pins in 1, 2, 3, the outputs. You can left click on the bottom here and you'll see it connects all three at the same time. It's a quick way of doing it. So there we go. We've got our solver and everything in here. I like to change the visualization to points. Press play, see it come down, splat on top of our sphere, and we can see what's happening as it runs around the tangent here, then shoots off. So just stop that a sec, go to sort of side view. If we come in, see as it comes around the edge here, it just kind of carries on cascading off at this angle, which is kind of the tangent at that point. Tangent sort of lies along the edge of the surface there. So it's not really sticking, and it's the sticking that we're after. So just to show that, if I go to the collisions here and turn on stick on collision, I'm just going to increase the stick scale to 0.3 so we can see an effect. And what I might do is let's drop the tangent scale down. So the way these work is the stick scale is sort of how strong the force is generally. So higher numbers will make it stick more. Also, the max distance is how far in scene units from the surface, that's here, that it's going to be affected. So that's going to be 5 centimeters, which is plenty of distance. You can also turn that off and use maximum cells, which is the number of voxels. But that's dependent on the resolution of your sim. I like the max distance, and that's keep that on. It's the defaults are pretty good. And then we've got these two forces, the normal scale and tangent scale, and then we've got a bias which kind of mixes between the effect of one and the other. So essentially, let's have a little look. So if you imagine a sphere, so a normal is a little vector that points out 90 degrees to that surface. So we'll call that the n. And then the tangent is the line that goes at 90 degrees to that normal, that tangent, so tangent there. And the tangent shows us the sort of curvature of the surface. So the tangent is sort of perpendicular to the surface to which it touches it. So if you think about it, the normal scale would be the force along the direction of normal, and the tangent scale would be the force along the direction of the tangent. So if we have a high normal force, we're going to push it in towards the surface, and a low tangent is going to be allowed to slide around the surface, slide a bit around the surface. Whereas if we have a high tangent, it's going to keep it stuck to the surface, and a low normal will allow it to sort of drift away. And you can kind of balance between these or mix between them as you see fit. So these are the sort of 3 parameters I mess with: the bias, the tangent scale. So the normal approach would be to do a few tests with this. So to put some different numbers in. So look, I've made this one big and this one small. Let's have a quick look and see if we can see the effect of that. And then you might tweak these numbers. You might switch them around and make the scale small and the tangent scale big. See the result of that. So here we're going to get a nice normal scale pushing it in towards the surface, but little tangent scale, so it's allowed to flow around, kind of thing. So that already you can see it starting to cling a bit at the side here. It's not flying off at an angle like we saw before. It's kind of hugging it a bit, and then it's kind of falling off, which is quite a nice effect. Actually, it's quite good numbers, I think. So already we can see it's a difference. Likewise, if we switch those around, go to the opposite extreme. So now we've got a very high tangent scale that's sticking it to the curvature, but still allowing it to flow with the normal. You'll see it looks much more viscous. And if we put both up high, again, it looks even more viscous, sticking to the surface. You could do that with a viscous effect as well. And again, if I bring down the stick scale, it won't have such a strong effect. So it slides over the surface again. Let's put it back to 3. So as you can see, you're going to have to do lots of different tests and check out the results to find out the sweet spot numbers. Now I could tell you the numbers that I've come to decide, but I'll just show you how I've come to decide on those. So I'll just show you what I created. I created what we call wedge tests. So let me show you this little QuickTime, a bit smaller. So what we can see here, wedge test, just, oh, that bottom bar's in the way. Let me just try and play that with a different viewer. Don't have that bottom bar. Go smaller. So what you can see here is what we call a wedge test. So a wedge test is a bunch of tests with different parameters, and we put them all together so we can compare them. The history of that actually comes from optical printing and traditional filmmaking, where we didn't know what exposures we'd need for doing complicated stuff. So we'd run lots of tests or wedge tests where we'd wedge the exposure to different amounts, and then we'd compare them all to decide what to finally do. But that's been taken over in 3D graphics to mean doing lots of variations of simulations. So what you can see here are the different parameters that have been played with. So at this top here, I've been keeping the normal scale to 0.1 and the stick bias to 0.5, but I've been playing with the tangent scale. You'll see the tangent scale increases here, and you can see the effect of that. On this next row, you'll see that we're now also playing with the tangent scale, but we've got a slightly higher normal scale. And again, across we're playing with the tangent scale, and at the bottom here, we've got different stick biases. No, I think they're the same actually. No, we've got a higher set of normal scale. That's it. So yeah, the normal scale goes 0.1, 0.5, 0.9 down, and tangent scale goes 0.5 across. And they're all for the stick bias of 0.5. And you can see by looking at them which effect you would like. So actually, if I look down the bottom here, this is the one I kind of like, where the normal scale is quite high and the tangent scale is quite low. And this is the effect I want, where it's hitting, coming around, sticking a bit, then falling away. So I'm going to show you in a minute how to set this up, which is quite handy, and then you can work through your own variations and find out which sweet spot you like. This is where I got to the numbers I wanted, high normal scale, low tangent scale, and a stick bias. I then took this a little bit further. I then realized I wanted these numbers, a high normal scale, a low tangent scale, and then I played with the stick bias. You'll see we've got 3 variations of the stick bias now, 1, 0.5 and 0.9, to see the difference in those. And you'll see with it quite low, it's really not having much of an effect. With it at the default, we can see a strong effect. With it very high, we see a much stronger effect. So I was quite happy to go with sort of this middle one, some value around there. And then what I did another wedge test here, where I was working out the subframes, the sub-steps. So here I've got the normal scale fixed at 1, tangent scale at 0.1, stick bias at 0.2, and then the only difference between these 3 now is the sub-steps in the solver. And you'll see by increasing the maximum sub-steps of the solver, again, the effect is more pronounced. And ideally, you want a higher number of sub-steps because you're going to get better fidelity. It does slow down the sim, but it does make things look a lot better. And I would always recommend having at least 4 sub-steps with your flip sim, because things like your stickiness and other stuff will be more effective, essentially. You don't use such high numbers to get them to work. Plus, like I say, you'll resolve forces and velocities much better. Things will just look nice. So here the sub-step should be between 4 and 6 really, I think, for this effect. And what I'm happy to do is the scale of 1, a tangent scale of 0.1, stick bias of around 0.2. So somewhere between here I'm going to use as the final settings for my fountain. So in order to set up the wedge test, what we first need to do is we want to be running various versions of the simulation simultaneously, and then we're going to composite those, automate those flipbooks and composite all inside Houdini using tops. But in order to do that, we need to be able to cache out our fluids. So for that, I'm going to create a fluid compress node. If you remember, this just makes the data on disk cheaper for us. So we can leave the defaults here, be good. And then we want a file cache node. So we can write out each one of these simulations. We'll just call this flip. And then we'll do a particle fluid surface. Fluid surface, we can visualize, or at least have something to flipbook. Wavelets or whatever. That. There we go. Let's display the particles. Oh, it's displaying the surface. Let's change this to particles. I'm going to put visualization to velocity. So if we run through, we'll see what's happening there. Now I want to run a flipbook of this. So what I'm going to do is I'm going to hit tab and type merge. And I'm going to merge the collider with the particles. There we go. So we can see it together. And let's find a nice angle, something like this will be good. So we can see the offset nature of it. So an angle like this. I'm going to hold down Control, left click on camera. If you hold down Control, left click on camera, it drops the camera you want. You'll notice the camera's locked, so we're still positioning the camera. I think that's the position for our flipbook, so we can see what's going on clearly there. Lock the camera so I don't accidentally move it. So you want to position this so that if you're running a flipbook, this is what you would see from it. I'm going to turn off the grid here. And we've got a cache, so we could write out a cache of this. So just to recap, create a fluid compress node, a file cache node, which will flip, and then particle fluid surface node here at the end. So what we want to do is we want to automate changing these three variables, and we want to automate running the flipbook and then compositing it into a QuickTime movie as we saw before. So we can do that through tops. So let's hit tab and type topnet. So topnet will create a container, whereas inside we can make a top network. So with a top network, that's task operators, we can build a list of tasks we want Houdini to do. So the first thing I want to do actually is to set up a bunch of caches with all those different parameters. So one set of caches where I'm basically, if we go back here, so one set of cache for this value, one sim at this value, one sim maybe at this value. So I want to see what happens if I keep these two the same and I vary this. So I'd want to sort of maybe have three versions of tangent scale, 0.2, 0.5, and maybe 0.9. So we've got a very small one, a very big one, and the middle one. And then we can also do the same for this normal scale. So we have three values of this and three values of that. That will give us 9 different possible combinations. And so I'll only have 2 of these variations for now. Let's put the stick bias down a little bit. Let's put something like 2.5. So I've just reduced that down a little bit. We can play with that variation a bit later, but for now we'll do 3 of these and 3 of these. So if you think 3 of these versus 3 of those, that's 9 different combinations in total. So we're going to run 9 flipbooks and then composite them. So let's look at how we might set that up. Now let's think of the parameters we want to change. One's called normal scale, one called tangent scale. So let's go inside the topnet. So the first thing we need to do is tell the topnet we want to create these wedges, and Houdini uses the same terminology, wedges. So if you hit tab, you can type wedge, and we get the wedge SOP. So the wedge SOP is fairly easy to use. What we want to do is first of all tell it how many variations we're going to have. And we said there's 3. We want to make 3, and that's this wedge count. So let's put 3 in, or you can drag the slider. Then we need to tell it which attributes here that we want. So we need to make 3 slots here. You'll notice it's not automatic to make those slots for you. So if I change this back to 0, you'll see these slots don't change. These should kind of be linked, really. The one that's important is this. Even if I set this to 1, it'll only listen to this first slot. If I set it to 3, it will listen to all 3. So even though you might have these filled out, if you forget to set the number up here, it'll ignore the other ones for you. So let's put this to 3. So the first thing we want to do is give it a name here. So let's call this norm scale. And then the other one I wanted was tan scale. And I don't need a third one, actually. So let's get... oh, that's not true. Let's get rid of that entirely. Yeah, my mistake. Yeah, when we hit 3 here, we don't want to add the 3 here. These are for different parameters that will run 3 times each. Well, what this 3 actually means is 3 variations of each one of these wedges. So if I did actually add another one of these, that means 3 of this and then another 3 of this. So that would give me 6 in total. So where this 3 refers to is the parameters here. So at the moment, I've set this to a range. So it's going to give me 3 values between this range. And it's going to do them uniformly. So that'll probably give me 0.2 or 0.25, 0.5, 0.75, something like that. If I put 5 here, then it will give me every 0.2, 0, 0.2, 0, 0.2, 6, 8, whatever. So what I do is I do want 3 wedges, and we don't want to do it by a range. We could do it by a value list. So here I can add in my 3 values manually. So now I can definitely say 0.1, 0.5, 0.9, and these are my 3 wedges that are specified here. So now if I do 1, it's only going to listen to the first one. If I do 2, it will listen to these first 2. If I do 3, it will do all 3. So you can do it from a value list, or you could do it from let it choose from the range. You can turn on random, and then it will choose random values between that range, but only 3 of them. So you've got various different options here that you can do. So the value, you'll just get 1 value, but a value list allows you to do 3 values. And a bracket, again, will give you 3 values around the center, so around 0 with an offset of 1. So you'll probably get 0, +1, then -1. But here, if you do a value list, you can be quite explicit about which values you want. So we want 0.5, 0.9. We also want the same for the tangent scale. So I'm going to make a copy of this, plug that in, this one, tan scale. And these names are important. I'll come back to those in a minute. So again, this wants to be 3 wedges. So we're going to get 3 wedges of this versus 3 wedges of that. So each one of these will generate 3 of these, and that'll give us our 9. So for the first 0.1 here, we're going to generate 0.1, 0.5, 0.9, the second one. And then for this 0.51 of this one, we'll generate 0.1, 0.9 of the second one. And finally, for 0.9 of this first one, generate 0.9, that which gives us our 9 variations. Hopefully that makes a bit of sense. I think we can preview that actually. If we go to, where is it? Generate node. You'll see here that these 3 jobs have spawned these 9 jobs. So if I click on that one, you'll see that's the first 0.1, 0.5, 0.9. This second one generates the next 0.1, 0.5, 0.9. And this third one generates the next 0.5. You can have a look at the information. It doesn't really show you very much actually. It just tells you which attributes are connected. Things like that. So that's quite handy. You can preview what's about to happen, whether it's cascading the jobs nicely. So if I told this to only do 1, and I regenerate this node, you'll see it's only doing the first one of each. So this one's only relating to the first one, the next one's relating to the first one, the last one's relating to the first one. So this is where you probably want 3 here. So when you generate the node, get all your 9 variations, which is the most useful way of doing it. So now that we've got that, this has set up all those combinations. What we need to do is we need to tell Houdini where to use this number. Now we can treat these like variables in Houdini. I'm just going to copy this name, tan scale, and the other one is called norm scale. If we come up here, we want to apply them here, where it says norm scale and tan scale. And we can do it simply with the at syntax. So here I copied the tan scale. So if I do at tan scale, Houdini will know that that is an attribute from tops and it will read it for us. And we can do here at, we call this one at norm scale. Now you'll notice if you click on the word, you'll evaluate the numbers. It's because we've evaluated this network here. Because we've told this to generate the node, it's done the first numbers for us. You'll see we've got the first sort of parameters coming in, kind of thing. But generally, you don't tend to see the numbers here. You just can put the variable name. So that's going to work. So at tan scale, at scale. So we now have programmed this to use the variables from the topnet to change these parameters when we run the topnet. So what I can't really do is run the sim now because it's going to give me an error saying it doesn't know what those numbers are, but that's fine. So the next thing we need to do is hash out each one of these 9 simulations we've now got at this point. And to do that, we use a ROP fetch. The reason we're using the ROP fetch is because this is going to fetch the ROP node. And we've got a ROP node here in this file cache. So we're telling it to fetch here and then write this to disk. We're going to automate this guy here. So the first thing we need to do is find out the ROP. Now this isn't actually the ROP. This is the file node. If we go inside it, you'll see it's actually made of a topnet. And here, this is the important one, the one that says render. This is your ROP geometry output. So this is the one we're going to trigger from tops. So what you can do is you can select this node and do Control C. We're not going to paste the node. We're going to go back in here. And where it says ROP path, you can do paste. And it will paste the path to that node. But if you click on the browser, you'll see it takes you to that node. There it is. It says render. Look, it's inside the file cache. It's the one that says render. You turn on relative path, just changes that to relative path, which is slightly easier to. So now we're rendering in that ROP. If you go to frames and batching here, this is the other important thing you want to do. You want to change this to frame range. Now you can specify the frame range in here of what that ROP's going to run. In fact, I'm going to change the time slider down here from 240 to 50. So down at the bottom right here, you can change the number from 240 to 50. We only want 50 frames. We don't want to simulate too many frames of this. And I want to simulate them all in one batch. This is a simulation. So with simulations, you have to simulate all the frames in one go. If you don't do that, it will send off each frame to a different machine. And that's not what you want to do. I mean, it's very efficient for rendering frames and rendering images, but not for sims. For sims, you need to do it in one go. So you must make sure all frames in one batch is turned on. You can also make sure on the file cache here that simulation is turned on. That's the same thing. That means use one process to simulate the whole network there. Now, the thing is, when we come to run this in a minute, this is going to go through and basically write out that simulation. Now, if I come up here and look at this file path, it's going to overwrite the same frame again and again and again. What I want to do is actually have this write out a different cache, each one of these different 9 simulations in the wedge. Now, when we run a wedge, this node generates an attribute called a wedge index. So that lets us know if we're wedging wedge 0, wedge 1, wedge 2, wedge 3, 4, 5, 6, 7, 8, 9, or 8 in this case, 0 to 8. So that's the wedge index. And we can use that wedge index to give us unique file names for each of the caches. Okay, so when you run a wedge, each of these wedges has an index, so we know which job we're doing, keeps track of the jobs. So this is the last one of the wedges here, and you'll see we have 9 of them. So we'll have indexes 0 to 8. Do we get to see that on the info? So yeah, there's the wedge index is number 3. So if I look at this first one, so you'll see the wedge index is 0. You'll see the last one, the wedge index is, where is it, 8. So that's our 9 wedge numbers. So we're going to use that wedge index variable to give ourselves a unique file name here. So to do that, I'm just going to change this to explicit. And what I'm going to do is I'm going to write out to where my HIP file's saved. And let's actually make a directory called Wedges. So if we make a directory called Wedges, then we know that anything put in that folder is actually our wedges, and it's going to keep things nice and tidy. And then if we want, we can just delete that whole folder. So I'm going to put everything to do with my wedges in the folder Wedges here. What's nice about these nodes in Houdini, if the folder doesn't exist, Houdini will make it for you. So in the file name itself, actually, let's put it in a new folder here. So we're going to copy it to a geometry folder. So in Wedges geometry, let's make another folder called index. Let's call it wedge underscore. So I'm going to call it wedge underscore, and then we'll put a back tick in. So this is next to your 1 key or above your tab, and then we'll use this variable at wedge index. There we go. Don't forget to close your back ticks, and then let's put another / in. There we go. So here we can make it a folder called wedges, and then we've got another folder called wedge underscore, and then we're using this back tick wedge index back tick. So what that's going to do, it's going to create a folder called wedge underscore 0 for the first wedge, another one called wedge underscore 1 for the next wedge. So we're going to get a unique file here for each one popping back in, which is going to be really handy for us. Let's turn on load from disk. It's not going to find that, obviously, because that doesn't exist yet. I'm going to write that to disk. So hopefully that makes sense. We're using the variable wedge index from tops, and just like we did here, we're using this at syntax, and Houdini is clever enough to know that where are we? That these are variables from tops, or from our wedges. So remember, the wedge index will be 0, 1, 2, 3, and so on, depending on which wedge we're running. So we've got our ROP network set up, ready to go. Now's a good idea to save. So the next thing to do is, if you can imagine, we've created our 9 wedges, each one with a unique index. We've now simulated each one of those 9 simulations. We've cached it to disk. What we want to do now is run a flipbook. Now, to do a flipbook is quite easy. We need to use an OpenGL ROP. So let's create a ROP for us. If you hit tab, you can type ROP, and you can make a ROP network. This will allow us to create a ROP context within this topnet, and here we can create an OpenGL node. So let's double click that ROPnet, go inside. So inside here, if you hit tab, you can type OpenGL. So this ROP will allow you to output basically flipbooks, and it's got similar settings to those. So what we want to do is we're going to trigger off this once for each one of those caches. So what we want to do is tell it to render the frame range here, and we want this to be frame 50. We only want 50 frames, so that's what we're caching. We need to make sure we've got the right camera, and we do, camera 1. And we can force the objects here. I've only got the one object in there, so I can pretty much leave this as the defaults. The other thing I want to do is just go to output here. Let's look at the output. Let's change the color correction to open color IO. Let's just switch this to ACES CG, because anything you do in here is basically ACES CG in 3D land. So we'll leave it at that. The other important thing is this output image. So again, at the moment, this is just going to run it to mplay. We want to save this to disk, because in the next part in tops, we want to load each one of those flipbooks in and do something to them. I'm just going to drop the JPEG quality down to 98. This actually makes it compress a lot more. No, we're not going to be writing out JPEGs anyway. No, that's fine. I'll probably write out PNGs because they're quite small. So what I want to do is steal that path. Where are we? Let's go to the file cache flip here. And I'm going to steal this beginning part of the path here. Let's do Control C. And let's go into our OpenGL node here, I'm going to just paste this in. So here, I'm going to go where the hip file is, or wedges. Now in here, instead of geo, let's call this render. So again, in the wedges folder, it's going to now make a folder called render. The reason it makes the folder is because it's got this ticked, create intermediate directory. And then what we're going to do is, again, we're going to create a folder for the wedge index. And then we'll just call this render.$f4.png. There we go. So again, we're going into the same database, the wedges database that we're going to create. This time a folder called render. And again, the wedge index thingy going on. So we get wedge 0, wedge 1, wedge 2, etc. And here we're going to get the we're going to call it render, whatever, $f4's 4-padded numbers.png. So again, using a similar path thing, or more importantly, the same database here. So now we're going to end up with a folder for each wedge with our individual flipbooks in. Otherwise, you end up overwriting the same one each time. So what I'm going to do is I'm just going to select this OpenGL and do Control-C, select this node. Because what we need to do is, in order to run that, we need another rock fetch. So here we go, we have another rock fetch. And this time in our rock path, we can either paste in the OpenGL node, or if you open it up, you'll find your topnet here, you'll find your rocknet, there's your OpenGL node. Let's turn on the relative path here. You can load it in that way. Now, what's interesting about this guy is we can go to frames and batching. Now, unlike the simulation here that has to happen sequentially, this guy doesn't. If we've got the frames, we can run this in parallel. We can run multiples of these at the same time. So I'm not going to turn this on all frames in one batch. We do want this as a single frame because it's going to run this once. But if you remember, in here, we told this to run 50 times. Okay. So this is the one that knows it's doing the 50 frames. So we only want it to run the once, hence the single frame here. What I do want to do is set this to 50. So that means there's going to be 50 frames in a batch. I'll explain what the batching is on a bit later on, because that it depends on how many processes you've got to how much you're going to split up your job. We'll talk about that in a moment. Let's carry on setting this up, but let's set that to 50 for the moment. So the next thing I'm going to do is add an overlay text node. So if you imagine now, we've rendered, we've cached out our geometry. Here we've run a flipbook for each one of those videos. So what this will do, this will overlay text or composite text onto each one of those videos. So if we go here and do generate node, it's asked me to save. There we go. What we can see here is we've got our 9 things there, our 50 frames. Here, if you click on these other tabs, you can see we've got more. If we go to the very end, you'll see there's 500 jobs. So, oh, hang on a sec, what does that say? So yeah, we've got 450 wedge jobs, which if you think about it, we've got 9 wedges of 50 frames. So that's our 450 jobs that we want to do. And then each one of those unique jobs, we're going to flipbook up. And then here we're going to now overlay some text onto each one of those jobs. And this is where we can tell it what those parameters mean up here. So it's a fairly simple syntax. Let's just get rid of that. So first of all, we just write in the name that we want to see. So I'm going to say norm scale, and let's put a semicolon in. And then we want the variable. So again, we do that with the backticks like we saw before. how we read it elsewhere in Houdini. Okay, so that's going to read the norm scale, and it's not vex, you don't need a semicolon at the end. We'll do the same for tan scale as well, at tan scale. Don't forget your backticks. So this will pop those in, and it will give us the relevant number for that particular wedge, which is pretty handy. And that will do the labels that we saw, the automatic labels. So, oh, hang on, before we move on, I just noticed I've got a capital N here. Let's make that a small n. I put a typo here, so we're going to make sure that is correct. So if we just check here, yes, look, it's a lowercase n and a lowercase t. So I just want to check I've spelt that right, a lowercase n. So yeah, we must change that, otherwise that's not going to work correctly. Oh, and the other thing we need to do actually is go to, where is it? Composite. And here's the size of the overlay it's going to do. And we want to replace this file name here. Otherwise it's going to overwrite the same file and it's not going to work. So I'm going to steal that again from the ROP network here. So let me just grab that path. Oh, don't need to, it's not sideways, it's up one. So if we come back here, let's just paste that in. So again, we're going to leave it at wedges. Let's call this, instead of render, overlay. And we do want the wedge index again, so we get a different one for each one. And we'll call this overlay.png, overlay. And each one will go in its own folder because of this bit like before. So that way we're going to get a unique image for each one of those for the overlay text. So if we generate the node for this, see we get 450 overlays. So each one of these is going to overlay with the text here. It's going to write this as the label, and then it's going to evaluate this variable for each one of those different wedges. So the next thing we want to do is take these 450 frames and montage them into the final format of the video we saw. So if you think about it, we've got 9 different sims and 9 different flipbooks. We've got 9 different frame 1s, 9 different frame 2s. What we want to do is take all those frame 1s and composite those into one frame essentially. So and then feed that into a node that we can composite it. Now the node that we can composite into is called the Image Magic node. If you hit tab and type image, you'll see Image Magic spelt with a CK. Now I don't think that comes installed with Houdini 20, but it's very easy to install. If you just go to imagemagic.org, you can click on download here and then download your particular version, your Windows or whichever version of OS that you happen to be using, Linux or Mac OS, whatever. Then you can install that and it'll set up all the variables, so it should work for you. And then if you do install it, you need to quit Houdini and reopen it again so it finds it. So at the moment, if we plug the Image Magic in, you'll see the default says, where is it, montage. And again, we're writing out an image sequence here. So again, we kind of want to steal the front half of the path that we were using. So this was going into a folder called Wedges. Was that uppercase? I can't remember actually. Yeah, it was uppercase Wedges here. So let's just change this to Wedges there. And then we'll pop this into another folder called montage. And instead of calling it the hip name and stuff, we'll call this montage as well. There we go. So again, we're bringing it into the folder and we're giving it an index here. Actually, let's give it the little folder bit as well, so they each go into their own folder. So let's copy that little folder section here. Just paste that in the other /. There we go. So in a folder called montage, each one's going to get their own. Actually, there is only one wedge index actually, because we're going to combine them all together. So we don't necessarily need that, but that's fine. Anyway, so if we just do generate this node, you'll see what it's done is it's kept our 450 here. So it's kept all of our 9 things. That's not what we want to do. What we want to do is we want to collect together all the frame 1s and treat those as one image, and all the frame 2s. So we should end up with 50 frames at the end here. You know, frame 1 has 9 flipbooks in it, and frame 2 has the other next 9, and so on. So to do that, we can actually use a partition by frame node. So the partition nodes allow you to sort out your jobs in particular ways. Here we're going to sort them out by frame number. So it's going to bunch together all the frames ones, and then it's going to bunch together all the frame twos, and so on and so forth. We right click on here and generate the node. You'll see it generates these slightly longer ones because you've got multiple frames here. Then you'll see there's 50 jobs now. So this is all the frame ones, all the frame twos. Now if I generate my image magic node, you'll see we're only compositing those 50 frames now. So these down into one frame, all this collection of frame twos all into one frame. Hopefully that makes sense. So partition by frame, and we've got that being montaged together. So the next thing we want to do is turn that into these 50 frames into a QuickTime. So again, if we do FFmpeg allows us to encode the video. So this does come installed in Houdini 20. If you've got Houdini 19.5, you'll have to go to the FFmpeg website and download a version. But with Houdini 20, it comes with the install, so you don't need to do that, which is pretty funky. The only thing we really need to do is just change these paths here, like we did before. So again, we'll do $hip / wedges with the uppercase W / this is called a frame list. We'll put that in the folder for frame lists, and then we'll just get rid of this part of the name. We'll call that frame list. You need the frame list for the FFmpeg to work. Again, here, hip video, let's do / wedges, so it goes in the wedges directory. It's going to be called video here. And then we'll just change this front bit to movie, something like that, and then leave it as an MP4 at the end here. So if we plug that in and we again to generate the node, you'll notice we end up with 50 QuickTime movies. We're going to get one QuickTime movie for each frame, which is not what we want to do. And we can't partition by frame now because all these frames are sequential. What we can do is use a wait for all. What a wait for all does, it waits for all these jobs to go through and then puts them as one job. We just want to feed it as one job into here to generate one movie. So if we generate the node now, you'll see these all concatenate down into one job. And if we generate this node, you'll see we get one QuickTime coming out at the end. So we've got our partition by frame, our image magic, our wait for all, and our FFmpeg encode. The last thing I want to do before I do this is to just change the codec. So the codec is here. This doesn't work by default with Windows video player, so I'm just going to change this to H.264 NVENC. There we go, so that's the top one there, H.264 NVENC. So that one will work with Windows Media Player. So I'm just going to save, and then we'll set this off. So we're going to right click and say cook this node. So that's going to take a while, and I'll come back to that in a moment. Now that has completed, we can see all the jobs have gone through here. So we've got our wedges, all our caches went through. You would have seen it went off simultaneously. We had our OpenGL, wrote out our overlay, our partition, and eventually the MPEG. If I double click the movie that it made, let's put that on loop. We can see our different wedges. We can see our normal scale at 0.1 across the top here, 0.5, and then at 0.9. And then as we go down, we're going 0.1, 0.5, and 0.9 of the tangent scales. So here both are high, here both are low. And if we look through, I can see the one I like actually is this one down here, where we've got a high normal scale and a low tangent scale. And as you saw from the other flip books that I've done, I did a couple of other wedge tests, which I preferred a few higher substeps of like 4. And I quite like the scale about 0.25 or about 0.3, just to fade off that effect a little. So we're going to go for this bottom left look here. But again, you could choose whichever look you like. The important thing is you can set up these wedges. You can go back up here and change some of these parameters, maybe wedge out different versions of the scale or the bias, and just compare them yourselves. But as I showed before, I've already got examples of those. So just to remind ourselves, let me just pop this one up. So here is the same sim again, and here's where I'm playing with the stick bias. So this is a low bias, a high bias, and this is about 0.5. So I was going to go somewhere between these two, about 0.4 or 0.3. And I'm going to go for a normal scale of 1 and a tangent of 0.1. This is why I did those 3 wedges. And then the last little test I did was with the substeps, just to remind you, we looked at these before. As you can see, as I increase the substeps, the effect is stronger. So I'm going to go for about 4 substeps or 5 substeps, depending on the speed. So those are the settings I'm going to use, and this is the advantage of kind of doing these wedge tests. So hopefully that's giving you an idea on how to do that. And again, you can just mix and match these, make a copy of this network and redo that. Just if you do change the parameters, don't forget to add in the overlay text here in the overlay section, add in your extra parameters here so you get the labels too. And don't forget to connect them here with the variables as well if you want to add more in there. Okay, so in the next video, we're going to apply that to our actual simulation.